Maddie Simpson with Simpson Math. In this video, we're going to use Bayes' theorem to solve a probability problem. So I'm at that age where it's time for me to start going and getting mammograms. And so I went to get one. And when I went into the doctor's office, there was a 1% chance that I have breast cancer based upon the prevalence of breast cancer in the population for women my age. I know that the prevalence or the occurrence happens about 1 out of every 100 women my age have breast cancer. So I went in, I had the mammogram done, and then a few weeks later I get the results in the mail and I have a positive test result. So then I want to know what's the probability that I actually have the disease, that I actually have breast cancer, once I got that positive result back into my hands. By the way, I didn't panic when I got that positive result because I teach Bayes' theorem, and so I wasn't too worried. Let's look at the probability that I actually have breast cancer once I get that positive result. So the probability a woman my age has breast cancer is 1%. A mammogram has a 99% sensitivity. In other words, 99% of the time, if you have breast cancer, it's going to catch it. It's going to give you a positive result. 1% of the time, it'll say that it's negative. You'll get a false negative. But most of the time, it catches it. And a 90% specificity. That means that if you don't have the disease, 90% of the time, you're going to get results back that say you don't have the disease. I went for a mammogram and my results came back positive. What's the probability I have breast cancer? Now, we could use the Bayes theorem or the Bayes formula to help us to determine that probability. I'm going to first make a two-way table and find the probability using that two-way table. And then I'll show you how we could have used Bayes' theorem or the formula to help us to find that probability. So when I'm solving these problems, I like to first make a two-way table. So there are two variables in this two-way table. I either have the disease or I don't have the disease. That's the first variable. I'm going to put that on my two-way table across here. Either have breast cancer or I don't have breast cancer. That's one variable. Then the other variable is when you walk out of the doctor's office, you either get a positive test or a negative test. So I'm going to put that variable here, a positive test, or we could get a negative test. And I'm going to put my data on this two-way table. So, and we have the total down here at the bottom. So I'm going to use my two-way table to help me to determine this probability. And then we'll use the formula. So the first thing we need to look at anytime we're filling out these two-way tables is our total. We want to know this total. So the total amount in my population. Well, my prevalence says that it happens in 1 out of 100 or 1% of the time. So I could say that 1 out of 100 women have breast cancer, which means that 99 out of those 100 don't. But I kind of want to make my population larger just to make my numbers a little bit easier to work with. So I'm going to make it, if I make it out of 1,000, then that means that 10 women would have cancer and 990 would not. Notice I just added a 0 to each one of those. I'd really like this to be 100 to make it nice and easy to work with. So I'm just going to add one more 0 to each of those, just so I have nice, pretty numbers to work with. Then here, a mammogram has 99% sensitivity. In other words, out of these 100 women who have cancer, 99 of them are going to walk away with a positive result. So 99% of these walk away with that positive result. So they have the disease, they get a positive test. But that means that one person walks away with a negative test, even though they have the disease. Then 90% specificity. In other words, of these 9,900 women that don't have the disease, 90% of them are going to walk away with a negative test. So 8,910 women walk away with a negative test. But 990 of those women without breast cancer walk away with a positive test. So the total number of women that walk away with a positive test is 1,089. Add across this way, and the total number of women that walk away with a negative test is 8,911. And my table should add up in all directions when I create that two-way table. Now, I want to know the probability that I have breast cancer given that I have a positive test. So this is a conditional probability. And that's why we can use Bayes theorem or Bayes formula on it as well, is because of this idea that it is a conditional probability. So if I were using my notation, I would say, what's the probability that I have breast cancer given that my test results were positive? So when I walked in, it was a 1% chance that I had the disease. But now I'm walking out with a positive test. So now my thinking has changed. All of a sudden, my thinking is not the same. I have a new probability. I'm only looking at the women with positive tests. So my denominator, instead of being out of the full 10,000, my denominator now is just out of 1,089. Those women with positive tests. And I want to know what's the probability that I actually have cancer. Well, the ones with cancer, it's 99 out of that 1,089. So in other words, the probability that I have cancer is about 9%. That means there's a 91% chance that I don't have cancer. So you can see this is the reason that even though I got a positive result in my hand, I didn't panic. While the mammogram does a really good job of identifying those women who have breast cancer, there are also quite a bit of false negatives that occur. Now, the test, once I got that positive test result, because going in to get another test is not invasive at all, I went in and did an ultrasound on my breast, and it turns out I do not have breast cancer. No worries there. But this is the updated belief, is the probability was 9% that I had breast cancer. Now that I've even had further testing, my Bayesian thinking kicked in, and now I know that the chance I have breast cancer is 0. So we change our beliefs based upon our new information. Now, with this same problem, how could I have used the formula to determine that? Well, using the formula is a little more complicated than just doing the chart. But the way we would do that is we're looking still at that probability that we have cancer, given that we have a positive result. And then what we do is we take the probability that we have cancer. Well, when I walked into the doctor's office, the probability that I had cancer was 1%, or 0.01. I'm going to take that and multiply it times the probability that we get a positive test given we have cancer. So in other words, what is that sensitivity? The probability I get a positive test given I have cancer. Well, that's that 99% of the time we have that. So the top there is just the probability I had it times that sensitivity, the probability that I get a positive test given that I have cancer. Then in the numerator, notice that when we did that, that's exactly how we got this 99 for our numerator. We first took 1% of our total, and then we did 99% of that. So to get this 99 on top, we did exactly that. We multiplied by 1%, and then we multiplied that by 99%. All right, now in the denominator though, we're gonna find the probability that we get a positive test. The probability I get this positive test. But notice that when we were getting the probability of that positive test, there are two numbers there. Because I can get a positive test from having cancer, or I can get a positive test not having cancer. So when I do this Bayes theorem on the bottom, I'm going to have two things that I'm going to have to add together. And so it doesn't look that way, but I'm going to have to first do to get this number, which was the probability I have the disease times that sensitivity, which we just did here. The 0.01 times that 0.99. Then, on the other part, in order to find out the positives that don't have cancer, well, that's the probability that you don't have cancer, which was the complement of that 1%, which is 99%, or 0.99. And then the probability that you get a positive test when you don't have cancer is also the complement of this 90%. The complement of that 90% is 10%. So I have to multiply that 99% times the 10%. And that's how we ended up with the 990, is we took this and multiplied it by 99%. That was 1%, this is 99%. Took this, and while we multiplied by 90%, to get that, we could have just multiplied by 10%. And then you add those two together. And it turns out that you end up with the exact same thing that we would have ended up with. We ended up with 0.0099 over 0.1089, which ends up being that same 9%. So for me, using the formula is actually more difficult than just making a two-way table. Seems simpler to me, but to each their own. Math Made Simple is Simpson Math. Thanks for watching.